And let's start going. We even have the front screen. Excellent. Okay, let me turn off these things. Can you guys hear me okay? You're not too far away. It's not like my hall where everyone's like a million miles away. Okay, so this is the last tutorial, unless you guys come up with something interesting you'd like to discuss next week. So what we're going to talk about today is parallel programming. Very quick introduction to it. We'll also be talking about it in lecture on Wednesday, and in particular, how you can apply it to milestone 4. Okay, so let's see here. Okay, so quick review of milestone 4. You've got this traveling courier program. So you've got a bunch of depots, and you've got a bunch of pickups and a bunch of drop-offs. You're trying to find the fastest delivery route. So part of finding the fastest delivery route is you're going to be trying to reorder the order in which you make pickups and drop-offs, and quickly figure out, is the travel time going up or down? So that's what we're going to talk about today. You're trying to estimate the travel time between all these locations in order to find a good delivery ordering. And you've got a time limit of 50 seconds. And it's what's called wall clock time or real time. So it's the time you're used to, okay? Not how much time the total amount of CPUs take. It's another definition of time that computers have. This is just time in the world. Okay, so we talked about this in lecture. You can estimate travel times in a few ways. You could use geometric distance. So if I want to go from intersection, some interesting intersection number 1, maybe that's my first delivery, to some interesting intersection number k, maybe that's my last drop-off, I could fill in a matrix where every row gives me what is the travel time starting at a certain intersection. So starting at interesting intersection number 1, and going to every other intersection that's interesting. So by interesting, I mean we got to make a pickup or a drop-off or it's a depot. All the other intersections we don't really care about. They're in the graph, but we don't really need travel times to them. And then the last row is for the last interesting intersection to all the other intersections. Okay, so if we have k interesting intersections, we have this matrix of k squared numbers, and that's all we need to compute travel times. So we could fill that matrix in really quickly by just estimating travel by distance. We'll assume we can just drive cross country at the speed limit of the 401, and we could fill this in. And that's not terrible. But as we talked about in lecture, it's not perfectly accurate. So if we could get the exact right travel time, well, this one is not interesting. That's from an intersection to itself. But from interesting intersection 1 to interesting intersection k, and so on, we could actually get a better solution because our travel times would be more accurate. When we worked out our delivery order, we do a better job of optimizing it. Okay, but it's slow. If we do that in a brute force way, it'll take too long. Okay, so how do we compute this travel time matrix? So first, I'm just reviewing things we already talked about in lectures. So you're going, hey, I know the answer to this. That's great. So in milestone 3, you wrote a pathfinding algorithm that goes from one source intersection to one destination intersection. Okay? And you could say find path with your best algorithm. And your best algorithm that you wrote in milestone 3 was probably an A-star algorithm. If you didn't get the A-star, that's okay. But let's say you did. And you could call it with that source and dest algorithm. And we have this double loop. And we'll be able to fill in every row and every column in the matrix by calling this. Okay, so let's say we've got k interesting intersections. Those are our depots, our pickups, our drop-offs. And in our graph of the city, we've got a total of v total intersections. So most of them not interesting. They're just waypoints on the way to getting between these interesting intersections. Okay, so let's see who's been paying attention. What's the complexity of this algorithm? Like the whole thing, this whole double loop and an A-star algorithm in the middle of it. So this will fill in my matrix. What's its complexity? Anybody want to take a shot at it? I'll give you a hint. I've only given you 2 variables. It's going to be a function of those 2 variables. So that's it. So what do you think? So let's break this down. How many times am I going to call this pathfinding algorithm? What do you think? Right, except I called it k this time. Okay, so which I like to change my variables sometimes, but so let's say that it's the number of interesting intersections was k, and you said k squared, right? Okay, so we got k squared times whatever this takes. What's the computational complexity of a single A star invocation? Anybody know? So it could go through the whole graph, and the graph has V nodes in it. In general, it might take, A star is kind of clever, so it might only go through a third of them or a quarter of them, but for complexity, we don't care about whether it's a third or a quarter. We just say could go through all of them, so that's V. And every intersection, the key work on it is putting it in the priority queue and taking it back out of the priority queue once it makes it to the top. How long does it take to put something in a priority queue or take it out of a priority queue? What do you think? What's the order of that? If we use a good priority queue. Yeah. Yeah. So it's log, and it's log of the number of vertices that we could have. Okay. So it's k squared log V log V. And it turns out that that's actually a bit slow. You know, you don't know exactly how slow that is for the problem sizes we're going to give you, but it turns out a bit slow. So it's k squared V log V. So k for milestone 4 can be 300 or a little more than 300. That's, and the intersections, the number of those can be hundreds of thousands, right, for this V. The combination of that means this is a little slow. Okay, so how do we speed it up? So we talked in lecture about Dijkstra's algorithm is actually a good choice for this. So A star is clever. It goes from the source towards the destination. That's really good if you want to go to one destination. But if you actually wanted to find from one source to many destinations, Dijkstra is actually better, okay? Because it just goes everywhere, and it can find you with one invocation of this multi-target Dijkstra, we can get the distance to all of the interesting intersections from one source. Okay, so we still, to fill that matrix in, we need a loop. We do have to loop over all the sources, which is k of them. We got k interesting intersections. But now we're going to call this algorithm, which is a little slower than A star, but only by a constant factor. That constant's not too big. Maybe it's 4x. Maybe it's 3x. It's not enormous. So with this one, okay, given what you know from the previous one, and knowing that this multi-target Dijkstra basically does, it's fundamentally very similar to A star. It just explores more of the graph. What do you think the complexity of this is? And if you're going, it doesn't seem, well, the obvious answer is this. It is the obvious answer. Okay, so if you look at this, you go, what do you think? What do you think the complexity is now? No, someone's thinking about it. Go for it. Right, so it's just k. It's k because we only go through this loop. There's only one loop, right? It's not two. So then we have, what is the complexity of this find, like this multi-target Dijkstra? So why don't you go for that? What do you think the complexity of that multi-target Dijkstra is? So it's, do you think it's different than A star? Or is it just within a constant factor? Yeah, it's basically, it can go through every single intersection in the graph. And for each of them, it puts it in a priority queue and it takes it out, both of which are log V. Okay, so it's actually a lot faster if k is big. Now, there is a constant, 3 or 4, but that's not going to be that big a deal compared to getting rid of that k squared. So this is better. Okay, so it's order kv log v. So we've got this better algorithm. Okay, so far I told you we were going to talk about multithreading. So far we haven't talked about multithreading. Why did I talk about this? Because this is the algorithm we're going to multithread. This takes a fair amount of your milestone 4 time, pre-computing these paths, which again, you don't have to do. You could use geometric approximations, but it's better to do this. And this is the best algorithm that I can come up with, or I think anybody can come up with. So you want to optimize your algorithm first, but there's no algorithm anybody knows about that's better than this one. So now you're basically, okay, my algorithm is as good as it's going to get. What can I do after that? That's where you multi-thread. Yeah. Oh, okay. So this is only a sub piece of the algorithm now. Okay. So this is me that matrix of travel paths, but from interesting intersection to another. That's just helpful to, that's an important component of finding a good travel order, but it doesn't tell you the travel order. Does that make sense? So when I say it's the best algorithm in terms of like how fast can I get all these paths, this is not my whole milestone 4. This is an important infrastructure component. Does that make sense? So yeah, so that's a good question. I don't mean to imply that you do this and you're done. You're not, okay? So, okay, so, but if we want more speed, we need to go to parallel programming. And I'm going to show you how fast these two algorithms are against each other, both multi-threaded and not in a few minutes. But basically, if I want this to go even faster, I need, the next step is to multi-thread it, to try to use more cores. So the UG machines you're running on have 4 cores. Does everybody know what a core means? Okay, so maybe I think I have a couple things on the next slide. Okay, so a multi-core processor, almost all processors nowadays are what are called multi-core. I'll talk a little bit about them in lecture on Wednesday. Basically, for many years, processors, you just kept making, essentially trying to run more instructions at the same time, okay? And that would make the processor faster. And the programmer didn't really have to do anything. The processor just ran the same program faster and faster and faster. And about 15 years ago, that started to break down, and it really broke down about 10 years ago. It turns out you just can't make, you can make processors a little faster still by running more instructions at once, but not much. The complexity of the power to do that is really high. When I say instructions, these are like the machine instructions that you're learning in 243. So a modern processor doesn't take the first instruction, complete it, and then do the second. They're actually running about 100 instructions at once. They do it in a way where it appears they all ran one after another, which is actually really, really complicated. So there's a lot of work that goes into that. And it's slowly going up. So today it's maybe 100 instructions at once. You know, in 5 years, it might be 150 instructions at once. So it's getting a little faster, but not that much faster. Because it just becomes too complicated and too much power for the processor to try to do more instructions than that at once. But the number of transistors we can stick on a silicon die keeps going up exponentially. So companies like Intel want to sell you better processors, but they can't make one that's that much faster for just what's called a single-threaded program, just doing one sequence of instructions. So what they did instead is they said, well, we'll make you multi-cores. So multi-core means you buy a CPU and it has multiple what would have once been called a CPU. Multiple cores, each of which can execute a stream of instructions. And they're not completely independent. They share memory, okay? So the UG machines have 4 cores. So basically almost like 4 CPUs, but those 4 CPUs are sharing memory, okay? So each one of these cores can execute its own instruction stream. So it could be a different program. This is why 4 people can be using the same machine and they don't normally notice much of a speed slowdown. Once the 5th person goes in there, you actually start to notice because now you're sharing, there's a pool of 4 things and there are 5 of you sharing it. But you can actually use all those cores with one program. It doesn't have to be 4 separate programs. So every one of these cores can execute its own instructions. So it can be doing a different thing. Could be a totally different program, but could also be the same program. And again, they all share memory. So that's why if somebody came onto the same machine you were on, you probably didn't notice much as long as they didn't use all the memory on the machine. If they tried to use all the memory on the machine, then you noticed right away because your program slowed down to a crawl. Okay, so I'm not going to go into much of this. I'll talk a little more about it in lecture, but this is a big topic. So if you want to learn more about parallel programming, in 4th year, there's a course called Computer Systems Programming. It's all about making programs go fast at the low level, like not really algorithmically, but how do you write really fast code? And a big piece of that is how do you write it so it uses multiple cores? And if you want to understand how do these cores really work with the shared memory, and how do we make these cores themselves faster? Because I just told you they're running, each core is actually looking at about 100 instructions at any one point in time. That's a big topic too. And you can learn about that in EC 552, computer architecture. And you can learn more in grad school. Okay, so these are pretty deep topics. Okay, but that's the big picture of what's going on. So what you've written so far, how many people have ever written a parallel program? So anybody, so you have actually, okay, so you've used some threads at least. So most of you though, it sounds like most of you have only written single-threaded programs, which is common, okay? If you get it done with one thread, you should, because it's easier. So far you've been writing programs with a single thread. So that means they've been running on one core. The other ones are just being used by somebody else, or they're just idle. And you basically have been going, I have all the memory, because your program, it's just one core. So that core basically says I got all the memory. I don't have to worry about anybody else. Okay. So you haven't worried about sharing memory because it has not been an issue for you. Even if someone else is running a different program, okay, so if that was Bob was running on this one, Sue was running on this one, the operating system isolates you from each other. When you get a seg fault, it means Bob was trying to access a piece of shared memory that he didn't know, okay? So the operating system took care of the shared memory. When you're two different people running two different programs, even though physically the memory is shared, the operating system allocates some to each of you and you can't get at each other's. So it does appear like you have the whole machine. So you've never had to worry about shared memory before. Okay, but now you're gonna, if you want, you do not have to do this, okay? So you can complete milestone 4 without any multi-threading. So it's completely optional if you want to use multi-threading. Don't use it right away, get a solution working, and then only do it if you want a challenge. But it is a very useful programming technique that you will probably use in your career. So you can start learning about it now if you want. If you're writing a program that uses multiple threads, then let's say we have 2 threads and they're going to run at the same time. Okay, we've got actually 2 cores now working and they both are getting at the same memory. And it is perfectly legal for them to get at the same memory. The operating system will not kill them, okay? So one of them can be writing to some variable and the other can be reading from that variable. Operating system is perfectly fine with that. Whether that makes sense or not depends on what your program's trying to do and how you wrote it. That might be exactly what you want. One of them's writing to a variable and the other's reading from it. That's how these 2 threads are communicating. Or it might be the exact opposite of what you want. You did it by accident and chaos is occurring. But you have to basically think about that. Okay, so you got to worry about it. And it's because multiple threads. So I could have a thread running here, and it's modifying some variable, and I have another thread running here, and it is maybe modifying or reading that variable as well. So whether I want to or not, they're communicating, and if I didn't want that, I've got a bug. It's a new kind of bug. It's called a race condition, where you're basically 2 things are reading the same variable without any coordination or thought of what's happening. Okay, so how do we parallelize? I'm going to take a really simple example, and we're going to go out and do a quick demo to see how it works. So I've got a for loop. Okay, so my for loop goes from 0 to 100. And all I'm doing is I want to add 2 vectors. So I got A and B, and I want to add them, make C. Okay, so I can run this. You know, I compile this, run it normally. What'll happen is you'll have 1 thread. So basically, like 1 program will go from 0 to 99 and do this, you know, 1 step at a time. So that's what you're used to doing. If I want to multi-thread it, there are a few ways that you can multi-thread things in C and C++. So the way that is easiest, like kind of the least code, is to use something called OpenMP. OpenMP stands for Open Multiprocessing. And you see, that's where this OMP comes from. Okay, so what I've added here is what's called a pragma. A pragma, you probably haven't seen this before. Has anybody ever used a compiler pragma before? Okay, so I wouldn't expect you have. What a pragma is it's like extra instructions to the compiler. If the compiler doesn't understand the pragma, it just ignores it, and your program will still be correct. Okay, but if the compiler understands the pragma, then it gives it guidance on how could you optimize this program or make it faster. So kind of extra information for the compiler that kind of doesn't get in the way. If the compiler didn't understand it, it's still okay. This is OpenMP is a standard that almost all compilers support. Okay, so this is we're using pragmas that are very widely supported, so we're not wasting our time writing code that probably most compilers will ignore. Yeah. No, well, pragma once is another pragma, so that's also information that's being passed to the compiler. But pragma once means just include this this header file once. Pragma OMP means I'm going to give you some information about parallelism. Keyword pragma is the same. Yeah, so pragma once is, basically almost every compiler now supports pragma once. But yeah, pragma once means only include this file once. It's a guidance to the compiler. You're right. And this is other guidance to the compiler. If your compiler ignores pragma once, your program probably won't compile. That's one difference, I guess. So pragma once, you probably really, really want the compiler to pay attention to it. If the compiler ignored this, your program will work. It will just be slower. Does that make sense? Okay, so this says pragma, so guidance to the compiler from the OpenMP family of pragmas. And the name of this pragma is Parallel4. Okay, so taken together, what this says is there is going to be a for loop right after this pragma, and I don't want you to run it normally with one thread. I want you to run it with multiple threads. I want you to split up the work. I want you to figure out how many, so this actually does a bunch of work for you. OpenMP, basically, this means split up the for loop that comes after this, split it up intelligently, so figure out how many cores I have, and split the work up across all of them, okay? So on the UG machines, we actually have 4 CPUs, and we don't actually have to tell that to OpenMP or to the compiler. OpenMP will check as it's running how many cores are there. It will find there are 4. So it'll say, okay, I was supposed to split this up across all the cores, split it up into 4 pieces. It will figure out how much work to send to each core. So we'll actually split this for loop into 4 pieces. It will send the first quarter to the first thread, the second quarter, so going from index 25 to 50 to the second thread. There's a third thread I'm not showing, and then the last one will get the work from 75 to 100. Okay, so this one pragma actually did quite a bit of work for us. Said, figure out how many cores there are, split up the work of the for loop that comes after. Does that make sense? Okay. So, and then what it also does is there can be code after this for loop. You know, your program could be doing some more stuff after this. OpenMP also says after this Parallel 4 only applies to the next for loop. After that for loop, we should all wait, okay? Because if I was running with one thread, you would have all 100 values computed here. I split it up across 4 threads, but I should wait for all of them to be done before I keep going. So after these 4 threads have each completed their piece of the work, well, they will wait until, so if one of them finishes sooner than the others, it will wait until all 4 of them are done. Then 3 of the threads will stop or be killed. Okay, they just disappear. And 1 will continue. Okay, so after the Parallel 4, your program continues running with 1 thread just like it did before. Does that make sense? So it's kind of pretty atomic. Run this for loop using all my cores, and then don't go on until they're all done and go on with 1 thread like you would have before. So as long as this for loop can be run in parallel, you're good. Yeah. What's that? Why would you not always? I'm going to show you some things that can go wrong. Okay, so if you just sprinkle this across every for loop in your program will crash. Pretty much guaranteed. Okay, so yeah. Yeah. So why do we have? Okay, so it's a good question. Okay, so the cores is the most important thing. So the UG machines, for example, have 4 cores. Okay, there's actually a whole bunch of shared memory on there too. Okay, so there's a bunch of memory in the middle. And then there's cores 1, 2, sorry, my writing's really messy. 1, 2, 3, 4. You will sometimes, so if you bought that, you'd pay 4-core machine. And you want to know how fast is each core, and I got 4 of them. And you also would want to know how much memory is there here, because these cores are all going to be trying to access memory, so it's actually important how much memory can they get at quickly. The UG machines actually can run 8 threads at once. So if you got the specs for them, they would say they're a 4-core, 8-thread machine. Okay, so how did I get 8 threads? Because I just told you that you can run 4 threads at once. Each of these cores can actually run 2 threads at once. Okay? In this particular chip. Okay, so this is different for different chips, but 2 would be a common number. Intel calls that hyperthreading. Other companies call it different things. They have different marketing names, but what hyperthreading means, I just told you that modern CPUs actually don't run one instruction at a time. They actually are running, they're looking at about 100 instructions at a time, deciding which ones to run, and they may be running, have 50 of them in progress at any point in time, and they're looking at about 100 to decide what to do next. If you can run 2 threads at once, what it means is for that 100 instructions they're looking at to run, they're not looking at 1 thread, they're looking at 2, okay? And those 2 threads can actually, so they can grab 30 instructions from 1 thread, 20 from the other, and they can all be working at the same time. Does that make sense? Now they're all sharing the same execution units. So maybe there's 1 divider. Usually there's only 1 divider per core. So they're all sharing that. There might be 2 multipliers. They're all sharing that. There might be 4 others. All sharing that. So when I run 2 threads on 1 core, I don't normally get at twice as much work done. So on the UG machines, you actually get about 1.5 times as much work done, okay, with 2 threads, because they do interfere with each other some when they're on the same core. When they're on different cores, they don't interfere with each other very much at all. But on the same core, they do interfere. But you could still get more work. So why don't I tell you to run 8 threads? Because the sysadmins have turned off that feature on the UG machines. So why have they turned it off? So you can only run 4 threads at once, because they turned off this hyper-threading feature where you could run 2 threads on 1 core at the same time. They've turned it off for security reasons. So this is now getting way off topic, but if you go look up Spectre and Meltdown, I don't know if anyone has heard those terms. These are security flaws that were found in hyper-threaded processors a few years ago, okay? One of my PhD students actually wrote a blog post on this, and they got quoted all over the place about, how they worked, because he actually went in and reverse engineered some of what was going on. There was a team in Germany that found the security thing. It's basically there was information leakage, and the information leakage is super subtle. It's actually timing attacks. They're trying to figure out what's in caches, which is on-chip memory. One thread, by trying to make various memory accesses, can try to put things in the cache or take things out of the cache. And by measuring how fast my thread is running, I'm guessing what another thread is doing. Did it already touch that memory or not? So there's a potential security hole where you could use that to figure out what some other thread is doing and guess passwords and so on. It is not an easy security flaw to exploit because it's so indirect, but it made the CPU vendors nervous, and they issued various security patches, and they keep upping their CPUs, like exactly how much isolation are they provide between threads. Our sysadmins for this generation of CPUs just said, we're turning it off because we don't want to have any risk. Does that make sense? Which might be overly conservative. And this is like an ongoing topic of research for computer architects. Hyperthreading is pretty useful for performance, but has these unbelievably brain-busting security issues that you have to think about. So anyway, does that answer your question? Yeah, go ahead. Oh yeah, sure. Cores is most important, number of threads. So you can, I guess a rule of thumb would be cores, count them all. If they say you have like twice as many threads, give half credit for all the extra threads. That's like my rule of thumb for hyperthreading, which is based on actually measuring things. And that's especially if you're not too worried about security. If you're really worried about security, then the extra threads are not worth anything because you're going to turn it off. Go ahead. Yeah. Yeah. Yeah, so notice that in this for loop, there's no dependency. What I mean by dependency is iteration 0 computes something, iteration 1 computes something, and iteration 1 doesn't depend on the result of iteration 0. So that's where you want to use parallel for, because you're saying it's okay to run these iterations at once. If I was adding all these numbers up, so if I was saying sum equals AI plus, well, sum equals plus equals AI, then a parallel for is not going to work for me because I actually have a dependency. My sum, there is another way to write that. It's a bit more complicated, but I can't just say run all these iterations in parallel because they're all trying to update the same variable sum. But this is the nice case where they're not. They're all trying to do things that are actually independent. Does that make sense? Yeah. Yeah. Yes, the constructor for thread. So under the hood, how does this work? These pragmas are making threads. And they would, if you look in the C++ standard library, and I'll briefly talk about this on Wednesday in the lecture, there is a threading library. And it has a thread constructor, which is how you make new threads. And this is making new threads for you, but it's doing more work for you. Like OpenMP makes life easier because it's figured out that you have 4 CPUs. It's figured out how much work this for loop does, and it's sending different iterations to different CPUs. So you could do that yourself by using that thread constructor, but you have to do more work. You have to go, how many CPUs do I have? You might hard code it to 4, but it's not as good. And how many iterations through the loop do I have? How much work should I give to each of them? Does that make sense? No, your program will still work. It's just there's no benefit. So sometimes you actually so not with OpenMP, well, not here. Like this parallel 4 is all about speed up. So OpenMP will use 4 CPUs because 4 threads because it knows there's 4 CPUs. It actually asks and it figures it out. You can run more threads than that because the operating system will time swap them. Okay, and so sometimes you actually want more threads because it helps you think about your program. For example, you might have one thread running your user interface and another thread doing computation, and you kind of want them to proceed independently. In that case, you might make 2 threads, not to get more done, but to just basically make sure that your user interface doesn't block your computation, or your computation doesn't stop your user interface from responding. And that'll work even on a 1-core processor because the operating system time slices it. It actually has one thread run for a while, then the other thread run for a while, and a while is like 100 milliseconds. So for a human, it kind of feels like they're running at the same time. Does that make sense? So you could actually, OpenMP won't do this unless you give it more commands, which you don't want to do. But you could say run 100 threads. It will work. It's not a great idea here. We're trying to get more throughput because there is some overhead to creating threads. So creating the extra 96 threads is not free, costs you some time. So it's kind of it's wasteful if you're just trying to speed things up, but it will not crash. Does that make sense? Try to make 1 million threads, you'll probably run out of memory and that'll crash, but 100 is going to be fine. Yeah, so these are all good questions. Any more questions on this? Okay. Okay, so I'm going to do a quick parallelization demo. Let's see. I'm going to see if people on Zoom can still hear me. I think they are. Okay, that's good. I think I mistyped that. Let's try that again. Okay, so let's see. Okay, so here's a really simple OpenMP program. Well, it's a C+ program with OpenMP. It's basically what I just showed you. So I've got 3 vectors, A, B, and C. So hopefully you guys can read this. Is this font big enough or should I make it bigger still? What do you think? It's good? You know, I think I should make it a little bigger still. So let me make this 18-point font. All right, hopefully that's a little easier to see. Okay, so I got 3 vectors, A, B, and C. I initialize them to some values, doesn't really matter. I'm going to ask what time it is right now. So I'm using chrono to get the time. And then I'm doing a parallel for loop. So notice I've got this pragma parallel for. What's my for loop do? It goes through the whole vector length. It asks, I'm just doing this so I can print it out, but I ask how many threads are there. You don't need that. I just want to ask how many threads is OpenMP creating. Normally I wouldn't do this. I just want to print it. And I compute some C value. So C, a certain C value for a certain index is just take the A divided by the B, multiply by 3, do a bunch of math on it. Okay, so it's like AI plus BI. I'm doing a little more math to slow the loop down. Okay, just adding two numbers is really fast. So I'm actually doing some multiplies, some divides, some modulus. Divides and modulus in particular take a bit more work. So one little more work in my loop, so it's makes more sense to parallelize. Okay, after I'm done, I ask what time it is. I print out how much time's elapsed. So I've done it over and over again. Okay, print out the time and print out how many threads. So let's go back and let's see how many. Okay, so right now my vectors are 10,000 elements long. Okay, so I'm going to do a bunch of work to compute a C value from two A values. I'm going to do it for 10,000 different array or vector entries. So let's make this. Should always do configuration equals release when I'm doing speed tests. So I just built this and now I'm going to run it. Okay, and it's really fast, okay? Because I'm doing 10,000 elements. CPUs are fast. It did it in 8 times 10 to the negative 5th seconds, and it used 4 threads. So OpenMP did do its job. Okay, now I'm going to go in, I'm going to turn off that. So remember that 8 times 10 to the negative 5th. Okay, so you have to remember that number. I'm going to turn off OMP parallel 4. Okay, OpenMP stands for Open Multiprocessing. Okay, so by doing that, my program just goes back to normal. 1 thread, serial, just like the programs you've always written. Okay, I'm going to run make again. I'm going to run, run this program again. Okay, now it's using 1 thread, but it's faster. It's 4.8 times 10 to the negative 5th, and with multiple threads, it was 8 times 10 to the negative 5th. So it's actually almost twice as fast when I used 1 thread as 4. So that seems kind of disappointing. Maybe we should end this tutorial right now and just say never use multiple cores, go buy a single core CPU. What do you think happened? Why is this slower? This is a real result, okay? This is like a real thing you need to be aware of, but why is it slower? So yeah, what do you think? Do you have an idea? Right. So there is an overhead to creating a thread. It's not free, okay? There is also some overhead. I showed you after all 4 threads are done, you have to wait, and then 3 of them basically die or do what's called going to sleep, and the other one continues. There's some overhead to that too. So we've got a lot of creation and destruction of thread overhead, and we don't have that much work to do. We had just 10,000 elements in our vector. It didn't pay for itself. So let's try. Okay, so there's an important lesson here. Do not try to parallelize little bits of work, because the effort to, well, the time to start the threads exceeds what you can save by using multiple threads. Also, it's a lot of programming work. I mean, we didn't have to write much code here, but it is harder to debug parallel code. So you don't want to do this for a tiny bit of work. Actually, I'm going to leave this commented out for now. Okay, so let's change this. This is just not enough work to be worthwhile. So that was 10,000 elements. Let's make it 10 million. Let's make it 100 million. Okay, so 100 million elements. This is still serial. Okay, this is the version where I do not use OpenMP. Okay, so I'm running this. And it took half a second. Okay, actually, I'm going to go up one more. I'm going to make this even slower. Let's count how many times. Okay, so it's got 100, 1, 2, 3. Let's do like 1 billion. So it's easier to read. Okay, so now we can actually, it takes enough time that we can actually watch it and get bored. Okay, so this is now getting a little more interesting. Okay, so that took us 4.9 seconds and it had 1 thread. So we read the output. Yeah, 1 thread's running, 4.9 seconds. Okay, so now let me go here. And I'm going to turn parallelism back on. Okay, so I'm bringing back my pragma parallel 4. I have to build again. And I have to run again. All right, so 4.9 seconds is the time to beat. See what happens here. And it took 1 second. Okay, so you notice the program took longer than that. I'm only timing the part that's parallel, right? So there was some build up of vectors and stuff before that. But the part that's actually doing the computation is parallel did get faster by actually even a little more than 4x. Okay, so that's actually slightly more than 4x faster. So it's good. We would expect, if everything's going well, 4x. You can sometimes, usually you get a little less than 4x. Okay, so this is a pretty good result. Why do we get a little more than 4x? It's probably due to caching. Okay, so each one of our cores has its own little bit of memory with it, and that sometimes can fit your data better, so you can get even more speed up than you thought you would. But usually you get a little less than you thought you would. Okay, so this is a very good result. Okay, does this make sense to everybody? So that's like our simple parallel program. It works, wasn't much extra code, and it's fast, as long as we give it enough work. Okay. So any questions on that so far? Okay, I'm going to keep going on that. If I can find my slides, let's see where they went. Let's move this down here. Okay. This is basically what we just saw. Some more numbers from it. So I'm not going to go through this. Basically, parallelizing can slow you down if you don't have enough work. Okay, so that was all a pretty simple program. So I told you this was useful for pathfinding. So basically, if you want to find all the best paths, compute that matrix, you're going to use a very significant chunk of your 50 seconds, okay, that you have for milestone 4. So even with the best algorithm that I showed you. So that's why multi-threading is useful, because instead of taking maybe 30 seconds or 40 seconds, you can get that down to maybe 8 or 10, and you have more time to optimize delivery order. So that's the purpose of why might you want to parallelize pathfinding. So here are some results that I already measured. I measured this on the Toronto Easy case. Toronto Easy has 25 pickups and drop-offs. So N in the lecture notation is 25, and it has 2 depots. So the number of interesting intersections, which I'm calling K, is 27. Okay. Actually, I think I screwed this up. If it's 25 delivery locations, I'll go check this afterwards. This actually should probably be 52, but it doesn't really matter. Okay. I think I did the math wrong. I'll go check it afterwards. So let's change that to 52 because I forgot to multiply N by 2. So I could pre-compute that matrix using my best single source, single destination algorithm, which was A star, and running it K squared times. So I showed that to you earlier. If I do that, it takes 32 seconds, okay, which is kind of a lot because this is not the biggest problem you're going to get, and we're already approaching that 50 seconds. So it's looking like maybe I can't do this for the big problems. If I rewrite it to do iterative multi-target Dijkstra, remember this one is going to do, we're going to have to run that algorithm K squared times. Whoops. Oh, what am I doing here? All right, let's not do that for a minute. Okay, so this is going to take K squared times. This one only has to be invoked K times. So it's a lot faster. So if I switch to multi-target Dijkstra, it only takes me 5.8 seconds. And we often call that a speed up. Speed up is just the ratio of the run times. So it's 5.5 times faster, 5.5 times less runtime. So algorithmic enhancement, very useful. Now I could take this iterative A star, right? So K squared invocations of that A star algorithm, and I could make it parallel because every one of those invocations is independent. So I could say, let's run that in parallel. If I do that, it does speed up. It actually sped up by 3.5x. Okay, not quite 4x, but pretty good. But it's still not as good an answer. If I look at the CPU time, it's not as good as the answer I got from changing the algorithm. And I can combine these things. I could take my good algorithm, this multi-target Dijkstra, and I could parallelize it. Okay, if I do that, basically the gains stack. My algorithm's better, and now I'm making my algorithm almost 4 times faster by running on 4 cores, compared to a basic A star algorithm running on 1 core. I'm actually 20 times faster. I'm down to 1.84 seconds. Okay, so that's fast enough that this will actually work fine for the biggest problems and still leave me a fair amount of time for optimizing my delivery order. Okay, so what's the point of this? Well, parallelism works on both these algorithms. It also means you don't want to parallelize first. You want to improve your algorithm first. And then if you still need more speed, then you can parallelize. If you do it in the opposite order, you risk writing a bunch of code where you sped up the wrong algorithm, which is not the right approach, right? It's kind of a waste of your time. Parallel code is harder to write. It's harder to debug. So you don't want to do it until you're happy with your algorithm. Does that make sense? Okay, so I've got this faster algorithm going. How do I make it parallel? So at a high level, here's what this multi-destination Dijkstra algorithm looks like. And obviously, I've deleted all sorts of code. There's lots of dots and so on in here. So interpret this as kind of, it's like pseudocode. I'm just giving you the high-level structure. So I've got 3 pieces of data that I've set up in advance. So we went through this already for how you write Dijkstra. You need a priority queue. So I'm calling that traversal queue. You need something that stores the best time to every node and how you reached it, what the reaching edge is. So I'm calling that all nodes. And then the last thing is I've got this new vector called key intersections. Key intersections is just, remember I said I've got like k rows and k columns in my matrix. Like I've got all these interesting intersections where I'm doing pickups or drop-offs or depots. So that's what this is. This just gives the intersection IDs of those k things. Okay, that's what I'm trying to find paths to and from. Okay, and I've gone off. I love global variables, but not really. Let's say I pretend, don't tell the other profs I said that. Let's pretend I'm a person who loves global variables. Okay, so I've made these globals. All right, so I've got this loop that basically says I'm going to go through all the sources from this key intersections vector. So key intersections, again, is all of the interesting intersections that I need, those k intersections. Multi-destination Dijkstra, basically you pass it the ID of some intersection, that's your source, and you pass it a vector of what are all the places you're trying to go to. So that's what I'm doing. I'm saying find paths from this source to all the intersections I want to go to. And I'm going to repeat that. I got a loop that I'm going to go through k times for every single source. Okay, so what do I, oh, and I'm using, people familiar with this notation? This is called a range-based for. So it's legal C++ syntax. Have you seen this before? Kind of looks like Python. So yeah, range-based for, in case you haven't seen it before, it's just shorthand. All it means is it's exactly the same as writing this. For int I equals 0, I less than this key intersections dot size, increment I, and the source is basically equal to that element, right? Key intersections of I. People write code like this often enough that C++ just said, fine, you can write this range-based for, and we'll just paste that in for you. So what I've written here is these are identical. Okay, so that range-based for does the same thing. Yeah. Would I be the variable that I is incrementing? Source is basically, so it's basically the range-based for has done both these things. I is incrementing behind the scenes. There's a hidden variable that's being incremented. And then you're getting the value that is indexed by I. And that's what you're using in the range-based for. Would you be able to access the value by itself? You don't normally do that in a range-based for. So C++ is complicated enough. I can't say whether there's some backdoor way to do it. But normally, when you write this, you're saying, I don't care about I. Right? I just want to get the thing that I indexed. So I was going to write this. This is shorter. I write that. And the compiler will write this behind my back. They're just the same speed. They're the same, basically. It's kind of like auto, right? The compiler's just filling in some stuff for you. Does that make sense? So I don't want you to be confused by this range-based for, but it's shorter, so I've used it in this kind of pseudocode. Okay, so, and then I'm calling, for every source, I call this find paths routine, which again just takes, what's the intersection ID of the source and a vector of intersection IDs that are all the places I want to go to. And I don't care too much about what that does. It's a Dijkstra algorithm. Inside my Dijkstra algorithm, I will for sure be sticking things in the priority queue. I will for sure be taking things out of the priority queue. Okay, so there'll be pushes and there will be pops. And I'm also going to be making updates to this all nodes because this is where I store my best time and so on. So all these variables, well, these first 2 variables are going to get modified in this routine. But I'm not showing you all the modifications. You kind of know this from what you wrote in milestone 3. Okay, so what do I need to do to parallelize this? assuming I had all the dots filled in, okay? So I guess you look at it first. You say, is there some part that I could parallelize? What you want to use for parallelize is there work here that's independent, that you could have two different cores, two different threads working on at the same time? If not, don't parallelize it, okay? If there's like a dependency, meaning I'm computing some data and then using it later right away again, okay, that's kind of a mess. Don't try to parallelize that. What you want is independent work. Could be split across multiple cores. So when you look at this, do you see any independent work? At least at a high level. We might have to fix a few things, but is there something that seems like it could be independent? What do you think? Yeah, so this for loop looks independent. It's basically finding the path from some source to all the destinations. And it does that for k different sources. The first source doesn't care what the fourth source does. So yeah, this for loop looks parallel. Looks independent, could be parallel. So let's write that. So we're going to say, make that a parallel for loop. And that's not much code. We just say, oh, pragma OMP parallel for, and now this for loop, the compiler is going to try to use multiple threads. More specifically, it'll actually try to use 4 on the UG machines. Okay, so that's looking good. And like added one line of code, so it sounds pretty nice. Is this going to work? What do you think? So in principle, this is the right approach. You know, if you went down here and you said, let's try to put some kind of parallel around this while, it's going to be a nightmare. Okay, don't do that. Okay, you won't get speed up. You'll have bugs all over the place because there's all sorts of dependencies inside that path search. That's going to be a nightmare. Don't touch it. But this is independent. So this looks pretty good. Okay, it's not going to work yet. We are going to make it work, but there's going to be something that goes wrong. What's going to go wrong here? Okay, this is a little more complicated than what we had before. We just had a nice for loop that was computing C, you know, C of I from A of I and B of I. So this might be pretty subtle. So I'll tell you in a second. But anybody have any ideas of what you're worried about? It seems like you're worried about something. What are you worried about here? Yeah, I've got one priority queue. I made a global priority queue. I made a global all nodes. I'm now saying run multiple pathfinding algorithms in parallel on different cores. That's going to call this routine. This routine there'll be multiple copies of this routine running at once on different cores with different source values. Okay? That seems okay, except look at this priority queue. I've got this priority queue. I've got one of them. Okay, this traversal priority, what I've called traversal queue, the wavefront. So just think of that as wavefront. I should probably change the name. I'll do that after the lecture. It's going back to this global variable. So if I actually have 4 copies of this code running on 4 CPUs, 4 cores, they're all using the same priority queue. Does that seem okay? What do you think? No, it doesn't seem okay. I mean, this is like you and 3 of your friends go to write an exam. We give you one sheet of paper. You're all writing exams from different courses, but you're writing on top of each other, right? Like this makes no sense. You go like, we're all going to fail. This is madness. Okay, we should not have done this. So it's not going to work. Okay, so these are shared variables. This find paths is using one variable here. Now that we have 4 copies of it running at once, it's kind of madness, right? We're putting data in our wavefront from 4 different threads, starting from 4 different sources, but it's all going in the same priority queue and getting shuffled and sorted. It's insane. There's just no possible way this is going to work. So how do we fix this? That might be hard for you to figure out. So I'm going to show you how to fix it. Okay. The way we fix it is we get rid of these globals. There are a couple of ways to do it, but the best way and the easiest way is we do what's called privatizing variables. So here we've got one copy of these variables, and if we have multiple threads down here, they're all going to use it. If we take these variables and we move their declaration basically into the parallel for or into one of the functions it calls, then every thread gets its own copy. Because every thread, so we've made 4 threads here in this for loop. And each of them is going to call find paths. And inside find paths now, we're actually making these variables, the traversal queue or the wavefront, and this data structure all nodes that keeps track of our reaching edge and so on. So every one of them actually now has their own variable because they made it. Does that make sense? They won't interfere with each other. It will now work. So it's a lot harder to make code parallel if it uses a lot of globals. So be careful of global variables. So any questions on that? Because that's actually pretty key. Okay. What about this one? I screwed up my animation so you can read what the answer is. This variable at the top, so let's say that was also a global variable. It's kind of bad style. There's no real reason I needed to make a global variable, but let's say I did it. This key intersections data structure. And you notice I'm looping over this key intersections data structure and I'm passing it into my find paths. This one's okay. So why is it okay? Because we don't write it inside these threads. We just read it. It's okay to have one copy of a variable that a whole bunch of threads read because they're not changing it. It's fine. Does that make sense? It's only when some of them are changing it and then the others are also changing it or reading it that we essentially have chaos. You could all be reading the same document online and often are, and that's fine. But if all of you are writing that same document online with no kind of orchestration, that is chaos. So you want to watch out for that. So this one's okay. Okay, so it was all right. Here's another question, which well, it's to illustrate a point. Let's say I didn't use global variables. Okay, because global variables, I shouldn't use them if I can avoid it. So let's say I now have a function called preload time matrix. So this is my building that matrix. That's our big task here. And let's say instead of having globals, I actually declare my priority queue and I declare this all nodes inside of it. Okay, I even declare this other variable inside of it. And then I have this pragma parallel 4 after it. Is this okay? So they're not global anymore. They're local variables to this routine. Is it all right? So what do you think? Key question is, does every thread get their own copy of these variables? And looking at this, what do you think? Is every thread going to get its own copy of these or not? No, I see you shaking your head. They won't. So they're not globals, but because they were created before the threads were created, every thread basically will be using the same copy. That's the rule. If these variables are created after the thread was created, so they're created inside this parallel 4 or inside of a subroutine that it calls, they all have their own copy. If it's created beforehand, they share the copy. Okay, so sharing the copy is fine with this one because they're all reading it, but is not fine with these two, okay, because they're reading and writing them. So these two, priority queue and vector of nodes, have to be moved further down, okay, more local inside of every thread. Does that make sense? Okay, so yeah, so local variables also are not okay if they're created before the threads and you're both reading and writing them in different threads. Okay. So I was going to do a demo. So we are over time. I think what I'd suggest is we just keep going for those who can stay, so I can show you what this looks like when you actually code it and what can go wrong. And then for those who just arrived, we'll go back. You'll see the end of the lecture before the beginning. Does it sound reasonable? Okay, so let me quickly flip over then to the other window. All right, so this is our reference solution for the basically everything in this course. So, all right, so this is basically, I'm not going to go through all the details of this because now this isn't pseudocode, and you guys should figure this one out yourselves. This is like pre-computing that big matrix. Okay, find all paths multi-threaded. So I'm just going to compile this, make sure it's up to date. Okay, and let's see, maybe I'll change it to release. All right, let's do that. All right, so I'm going to run one of the EC 297 exercise test cases. And I already know which one I want. Actually, I don't remember it exactly. Let's say list testers to get the names of the testers. Okay, so I want the one that has easy Toronto in it. So this is that test case that has, I'm going to see what my case should be here. Okay, so it's going through load map right now. Okay, it's got 25 deliveries. So actually K is 52. Okay, so the number of interesting intersections, 25 pickups, 25 drop-offs, 52 total intersections that are interesting. You see it, the path finding to compute that matrix took 2 seconds. So pretty fast, okay? I've got 50, so I didn't spend too long in path finding. Now, it's not the biggest problem. Now I'm going to go back, and I'm going to turn off parallelism. So I just comment out that parallel 4. I rebuild. And I'm going to go back, and as soon as it's finishes compiling, I'll run it again. Okay, so remember that number. Path finding took 2.1 seconds. So I'm running it again, same algorithm, I just turned off parallelism. So I expect this is going to take maybe around 4 times longer because I'm using 1 CPU, 1 core instead of 4. And let's see what it happens. Okay, so it took 5.5. I mean, the other one took 2. So it means I only got a speed up of maybe 3 in this case. Okay, maybe a little less than 3. So still good, but not as much. The speed up's actually bigger if I do bigger problems. So, but anyway, it's a pretty good speed up, right? So it was worthwhile. So now I'm going to turn parallelism back on. And I'm going to go over here and let's see. So I'm going to do 2 things. I just turned parallelism back on, and I'm also going to go to the top of my M3. Actually, let me go back 1. Okay, if I go through this, you're going to find that this calls, some helper functions. So I go into this helper function. I don't want you to worry about all of it, but basically this define here. Okay, so this is an if-def. If I turn on this variable, like I define this variable bad parallel global 2. Okay, so that sounds like not a great define to turn on, but I wrote it. What it's going to do is if I define this bad parallel global, it's not going to declare this local variable anymore. Okay, it will not declare my priority queue locally inside my path search. And instead, if I go back to m3.cpp here, which is where my pathfinding algorithm is, if I go back to the top of this file, let's see if I can grab this and go back up to the top quickly. Huh, what is this doing? Okay, so I go back to the top of this file. Yeah, what happens if I comment this out? Okay, so I'm going to turn off that define, and whoops, not that one. I want this one. So I'm going to define this, what's called a preprocessor variable, called bad parallel global 2. And what it's done is I've already written this code. It basically changed my priority queue from a local variable inside my pathfinding algorithm to a global variable. So I just did a bad thing, right? I have it written the right way with a local variable. I just turned it into the wrong way with a global variable. And now I'm going to recompile. I'm going to get some warnings. I'm going to ignore them because I'm a really bad programmer. Okay. So these warnings are actually telling me your code looks a bit funny. You've got some names that are hiding each other. That's because I just changed a local variable to a global one. So I'm hacking like mad. And if I actually pay attention to the warnings, the compiler just told me this is not great. If I go out now and I run this, so let's do an EC297 exercise. Okay, so what it is now is parallel, but I put a global variable back in my pathfinding algorithm for the priority queue. And we already talked about that. Does not seem like a good idea. So it's running. Let's see what happens. And it should fail. So unless I did this wrong. So hopefully I've turned parallelism back on. Let's just make sure I did. Yeah, I did. Okay. And I've turned off that. Okay. Let's go back here. So these can fail in all sorts of weird ways. Okay. They can crash. They can hang. It looks like this one is hung. And if I run this again, it actually might do something different because the threads are essentially racing. They're updating the same data structure, and every time you run them, they can actually update in a slightly different order. So for this particular one, you saw with no parallelism, it took 5 seconds. With parallelism, it took 2, and it's been going for a while. So this is hung. Okay, and if I run it again, it might not hang, it might crash. Debugging parallel issues is actually quite tricky. So I've already set up the unit test for this. So I copied them over from the public unit tests for this file. So I'm basically building the unit test so I can run the debugger on it, so I can see what's going on. Okay, so I'm now going to start the debugger. And I didn't set any breakpoints or anything because I actually don't expect this to go super well. I expect it to crash or hang or something horrible to happen. So load map's going to be okay. So load map is running right now. That should be all right. Okay, so at this time, last time it hung, this time I got memory corruption. So it says double free of corruption. I can say discard and pause, and I can go look at it. And I've actually turned on in window debugging. There's this extra window that I've turned on called threads. Okay, you probably don't have that on yet. So if I look at threads, it shows me I have 4 threads running. This GI raise means general interrupt raise. It means I'm dead. I'm going to tell the operating system I'm dead. I can look at its call stack to see where it is. It's in a bunch of stuff I don't recognize. So I go back to something I do recognize, and it's in the priority queue, which was called from here. Okay, so it's trying to push something in the priority queue, and I could actually go look at that variable if I wanted to. I can look at the other threads. If I double click on this one, I can see where is it in the call stack. It's trying to destroy something. We go to this priority queue, or so this thread, it's in the middle of trying to create one of these node data structures that I use. And if I go to the last one, it's also trying to create something. Okay, so this particular one died in memory corruption. 3 of the 4 threads are not in the priority queue, but the last one is in the priority queue. The corruption, so this is actually kind of difficult to diagnose. I probably have to run this a few times, notice that the priority queue, something tends to be in it all the time, but it's really subtle. Because we've had multiple threads trying to create and destroy stuff in the priority queue, they've managed to corrupt memory. So that's hard to debug. One of the things that I will do in that case is, let me go back to M4, is I'll turn off parallelism. So if you're writing parallel code and something goes wrong, you turn off parallelism. And I can do that just by commenting out this parallel 4. I'm going to rebuild. Okay, and I'm going to run it again. Okay, so it's running. And we'll just see what happens. Because I don't know what's happening, but as soon as I have parallel code, I think maybe I've got a race condition. Maybe more than one thread is accessing and modifying a shared variable. A quick way to check for that is turn your parallelism off and see if the error goes away. Okay, so I'm running the debug build. I've turned off parallelism. It's going to take a little longer, but it finished. Okay, so it took it 16 seconds to fill in that matrix with the pathfinding, and now it's on to the delivery order optimization. So it worked. So this is strong evidence that this is probably a parallel rated bug. So anyway, and I don't have time. I can show you lots more ways to crash it. If I turned on the, so I just did Control C to stop this. So that was me killing it. But basically, if I make that other variable a global, it will crash as well. And it'll crash in different ways. And if I ran that again, it could crash in a different way. So, okay, so when you're debugging parallel programs, good thing to do is disable parallelism, see if the problem goes away. If it does, it's probably what's called a race condition. Multiple threads reading and writing a shared variable. The best way to fix that, find the shared variable, privatize it. You can also run in the debugger, and you can use this window debugging threads view to look at what all the threads are doing. You can look at the call stack for each. And if they're all kind of dying around the same variable, it's a good sign that that might be the problem. Fixing race conditions is hard. Okay, this is a difficult debugging problem. The basic technique is privatizing variables. You find the race conditions, you give everybody their own copy. There is another technique, which I'll talk a little bit about in the lecture. There's another pragma called OMP critical, OpenMP critical. It means only one thread can execute this block of code at a time. So they will like serialize at that point. That's another way you can fix this undisciplined access to some shared memory. If you do this for everything, though, you basically make the threads all wait all the time, so there's no point. Okay, you'll lose all your speed up. So generally, what you want to do is privatize variables first. Okay, you only use OMP critical for a few variables that you really have to use. If you want to parallelize milestone 4, like the pathfinding part, you don't need any critical variables. You do not need to use this. You can privatize everything. Okay, and that's generally where you want to parallelize, is where it's easy, not where it's hard. Okay, last, I think I'm almost done here. You have to realize that also the speed up is limited by any remaining serial code. So there's a famous law called Amdahl's law, after Gene Amdahl, a mainframe pioneer. Let's say we have n cores, and F is the fraction of work that can be parallelized. So this shows what the speed up would be as you increase the number of cores. You know, from 1 core, you get time speed up is 1. And as you go to a really large number of cores, if only half of your program can be made parallel, then no matter how many cores you have, your speed up is no more than 2. Okay, it makes sense, right? The rest of it doesn't speed up. If 95% of your program can be made parallel, then you can get to higher numbers. You can get all the way up to 20x. But it's hard to get really huge speed ups. If you say, well, maybe I could have, like, in this case, 65,000 CPUs, what speed up could I get? Even if 95% of your code can be made parallel, you're still only going to get 20x. It's really, really hard to get these gigantic speed ups. Okay, so kind of takeaways from this. So improve your algorithm first. You can usually get bigger gains doing that, and it's usually less work. These OpenMP pragmas are a pretty productive way to make a program parallel. They're a little higher level than directly instantiating threads with the C++11 thread constructor. You don't want to modify state variables that are shared across multiple threads. Okay, so that minimizes bugs. So you do that by privatizing variables. Everybody gets their own copy because you declare it as late as you can, basically. You don't want to make tiny bits of code parallel because it isn't going to gain you anything. And it's hard. Parallel programs are fundamentally harder to write than serial ones, so you don't want to do it first. You want to do it last if everything's going well and you want to challenge. And then you don't want to parallelize things that are really complicated. You want to take a part where you go, the strategy to parallelize this is not too complicated because that's the one you might succeed with. So for M4, get something simple working first. You know, use a simple travel time estimate, like geometric distance, use a simple greedy algorithm, get a legal solution, and then start improving. Okay, so start getting better cost estimates, maybe with the path search algorithms we've talked about, do more optimization of your orders. And then if everything is working well and you want to further challenge, then you could go parallelize, but do not do this at the start. If you're not spending any time paying attention to your other courses, don't do it all because the instructors will get mad at me. So yeah, this is not mandatory by any means, and you should not do it as the first thing. You shouldn't go, that sounds really cool, I'll do it first. Do it last if you want to do it at all. Okay, sorry for going overtime. Thanks, everybody. Sure, and I'll answer any questions if I have to. Yeah, so the parallel for that I showed you, actually all the functions it calls are running in parallel. So even though the for loop looks short, that for loop has a function call in it. That function call is running in parallel as well. Does that make sense? Yeah. Yeah. Yeah, the function itself, you basically every one of the, if you have 4 threads and you've divided up your work, let's say we had 50 calls through that for loop. So each thread is going to get, let's say 52 calls. Each thread is going to get 13 iterations through that for loop. And as it goes through, if it calls a function, that function will be invoked by that thread. Does that make sense? You can put like parallel for inside parallel for. So you can actually, but you only have 4 cores. So you have to think about, why am I doing this? If you already have like 13-way parallelism, for example, or sorry, I've got 52 iterations that can be run in parallel, I've only got 4 cores. There's no real point in putting another parallel for inside of it. If you had 1,000 cores, okay, now that might make sense. But if you have 4, it doesn't really make sense. Does that make sense? Yeah. Thank you. You're welcome. Yeah. Yeah. If they're all reading, it's okay. So that's what that key intersections one, that's why that one was okay. You'd set it up in advance. Everybody reads from it. That's fine.
And do race conditions also occur for non-linked data structures like a vector?
Yeah. I mean, if you're pushing to the back of a vector and somebody else is reading from it, or you're updating one entry and somebody else. Yeah, same thing. If you're, yeah, anything. Could be an integer. Yeah. If I've got an integer and one person is saying increment the integer and the other person is saying read it, you don't know which order that's going to happen. Or even if they're both incrementing it, one of them can start incrementing it, the other's incrementing it, and one of the increments can be lost. Does that make sense?
Yeah.
So any modification of a shared variable without synchronization, so synchronization would be with the OMP critical, is unsafe. It will not work in general. So it might work sometimes by luck, but that's why it makes it really hard to debug, is sometimes it might even go, it worked, but that doesn't mean your program really works. Does that make sense?
Yeah. There is no legal path.
Yeah, you're supposed to return a vector that is 0 length for all the subpaths.
Yeah. I was just wondering, is there a legal overview? Is there a set way to define if a legal path just exists? Because like a legal path might exist, but it might be like super non-optimal.
It's okay if it's like arbitrarily non-optimal as long as it exists.
Is there a way to check like a path just exists?
Well, when you're doing your path searches, if your path searches fail, that's a strong indication that it doesn't exist.
So maybe
does that make sense?
Yeah, like we could have something like if all of our kind of heuristics fail, then check maybe a really basic way of just doing it non-optimally.
Yeah, yeah. I mean, basically, if there's no way to get from some intersection to the other intersections, then if it's a depot, that you can still survive because you can just use the other depots. But if it's one of the deliveries, then you're done. Because if it's just disconnected, so you find there's no path that I can find from this part to that part.
So it's more kind of like try a bunch of all.
Yeah, you can usually even tell, like if you compute this matrix, you'll find there's a whole bunch of like zeros in it. Or like it failed. Do you know what I mean? Like I didn't find any path from here to there. Does that make sense? Now with depots, that's not, a disconnected depot is not a hard failure because you can just not use that one. But a disconnected delivery, like I can't get from this delivery to, or this set of deliveries to this set of deliveries, you're done. A good test case for it is like the Toronto Islands, right? So Toronto Islands are not connected by any roads to the mainland. So it's a good test case. So, so I mean, you can make your own test case for that. Or you can make a little GUI if you want and enter it through a GUI. You don't have to make a GUI, so whatever you want. But if there's no UI. If you make a UI, it's for yourself. So So if you make a UI, you can show it in your final presentation. Maybe it's helpful to you for debugging, but you don't have to make a UI. We're not creating a UI, etc. Okay? You're welcome. Sure.
What is like the pragma on for difference from like the extent of like the way you declare it? Because I remember you declare it as a thread.
Yeah.
You put it in yours.
So I'm just going to stop the, well, actually, this is an interesting question on to have on the recording too. So the C++11 threads are essentially OMP Pragma Parallel 4 builds on top of that. All the OMP Pragmas behind the scenes, they're actually creating threads using C++11 threads. Does that make sense? C++11 threads actually builds on another library called pthreads. So they're really the same thing. OpenMP is creating those threads for you. So it's essentially one layer above. Okay, you could go write that code yourself. I'm going to make a thread with the constructor. Let's see, no. So